just want to introduce the work that I have been doing for the TI team. So we try to evaluate availability of empirical data to constrain the hanging wall scaling for small magnitude. And we have been targeting the Japanese data that Adrian Rodriguez-Marek and his colleagues have been compiling from the KickNet network. So as you know, there is a paucity of data existing in the hanging wall region to constrain the scaling. We need more data to constrain the scaling for the moderate to low magnitudes to compare with the hanging wall scaling of our candidate GMPs, and also to use this empirical data in the visualization maps that Nico has been showing us. So in order to be useful, we need to have at least a couple of stations located on the footwall and a couple on the hanging wall. And so you remember from Norm's list of tasks identified at workshop 1 and workshop 2, we had the task of looking into these Japanese data, and then if promising data exists, to perform a finite fault rupture model inversion to get a fault model, and then to fully characterize the rupture, and therefore to populate our metadata. So as mentioned before, we used the Japanese database put together by Adrian and his colleagues. Here you have the reference is a paper in preparation, as Adrian confirmed. So we wanted to restrict our selection to those events with magnitude 5 to 6.2. We are really interested in magnitude 5.5 to 6, that there is a paucity of data, but we wanted to expand a little bit more this range to see what is available. And then Adrian's database includes events associated not only with active crustal region, but also with subduction, and so we purged those events out. For the vast majority of the events in Adrian's database, the finite fault rupture model is not available. I would say there is an exception of probably 3 events, but they do not follow in the range that is important for us. So the metadata, for us, we don't have metadata associated to published finite fault rupture. So what we did, we looked at the FNet metadata that were compiled in Adrian's database. These metadata do not distinguish, they provide information for magnitude and hypocentral depth, but they also provide 2 distinct solutions for the 2 conjugate faults. So we have deep, strike, and rake that are varying according to the conjugate faults. So we had to get a way to visualize this data. So we derived an area from a magnitude area relation that you see here, and we imposed an aspect ratio 1. It means that our fault is basically a square. And then for each event and fault solution, we have inspected the stations to evaluate if they fall close to the hanging wall footwall region. So you see here the scheme. Here would be the down deep fault extension. So for us, the down deep fault extension and the length is the same. And then we had looked at a region which is more extended with respect to the projection of the fault on the surface. And again, for us, we wanted to increase the possibility to capture usable stations. We also have increased the acceptance area 5 kilometers along strike in both directions. So you see here in map view, that is what we have considered as an acceptance area. This would be the topmost part of the fault, its projections, its hypocenter. We centered the fault around the epicenter, the hypocenter. We didn't randomize the location. And then we consider an acceptance area, doubling up this quantity, this distance in the footwall portion, actually on the hanging wall portion, and then one R1 length in the footwall side. And then again, 5 kilometers on each side of the strike. So by applying this inspection, our results are not as encouraging, let me say, as we would have expected. Out of 75 events that were following in our selection, only a couple of them have stations that fall on the hanging wall and the footwall. Only one station per side for 2 events. So that doesn't give us a lot to work, and this is our best case scenario. There are other couple of cases in which we would have some stations but close to this acceptance area, but not quite inside the acceptance area. So given those, the way we imposed the acceptance area, these events would not be considered. There are other cases in which we only have one station, which is either on the footwall or on the hanging wall, and that really depends on which one of the 2 conjugate planes we are considering. But we are missing the part on the hanging wall or footwall, so that is not really useful for us. And also there is an event where we have potentially 2 stations, either on the hanging wall or on the footwall. Again, depends on the conjugate plane. But again, they would not follow inside the acceptance area. There are a couple of events that are well recorded, means that they have several stations that recorded the events, but unfortunately the distribution of the station is not favorable for our scope. The stations here are distributed mainly along strike, they do not follow in this region, and it's the same pretty much here. So these events are not really useful for us. So, and this is just another example of stations that are just all on one side of the fault, so that really doesn't help much. So at the end, our inspection showed that there are no usable events found in this Japanese data set that we received from Adrian Rodriguez-Marek. In the best case scenario, we have 2 events with only 1 pair of station, one on the footwall and one on the hanging wall. Again, given the acceptance area that we have applied. So the question would be, should we broaden the acceptance area? Would that make sense? I don't think that would make sense, but that would be a TI team call. And given the situation, it is unlikely that we would be able to recognize events that could help us constraining the hanging wall, footwall scaling much better. So that is a very quick presentation. If you have any question, please.
I realize that you're considering only the reverse fault case because that's applicable to Diablo Canyon. But if you want to compare hanging wall, footwall, it seemed like L'Aquila, even though it's a normal faulting event, is one of the best because it has about 4 stations sitting on the hanging wall and a couple that are right near the footwall right on the other side. And so, allowing for your normal way of handling style faulting and things like this, but if you want to make a comparison as to what it might be, it seems like L'Aquila would have been a good choice. At least it's well recorded, and there are a number of stations on the, that are on the hanging wall, and it's well covered. So
L'Aquila is in our data set already, so we've been using that one. So our goal here was to see, can we find some additional earthquakes? So that one we've got.
Okay, missed it.
And so we're looking for others, particularly as you get down into the smaller magnitudes, for how the hanging wall effect would taper with magnitude. And our thought was, all the reverse events in Japan, there must be some with good sampling close, on both sides and at close distances, and that's just not the case.
How about the L'Aquila aftershocks?
Well,
those are in that magnitude range, I think. Maybe low 5s. The L'Aquila aftershocks?
If there's anything in the NGA database, we're trying to add things.
To expand, we're trying to expand.
I'm wondering if it's in the NGA database. I'm not sure.
The aftershocks? There's a whole bunch of them.
They are there. Okay.
Yeah. You guys excluded aftershocks, so you didn't look at them.
We included them in the phase 3, but anyway.
So our basic conclusion is that,
The database you used was through 2011?
That would be a question for Adrian because the database was provided by him. So Adrian, can you answer that question?
I believe it's up to December 2011. Yes.
Yeah, I was just curious. I mean, that's pretty long ago now. There might be more.
Is there any plan, Adrian, to augment your database and put more recent event inside?
Not with this PhD student because he needs to graduate.
Okay. Okay, thanks. Okay. Oh, there is a question from Tom.
Just one comment, which is, although we don't have a lot of data, we have many observations of macroseismic effects. I mean, a good example would be from the Loma Prieta earthquake, and we know in the area above in the hanging wall that there were large numbers of redwood trees that had their top 10 meters snapped off, and that's the only place you found that. There were extraordinary stories of people being thrown through the air and pianos upside down. And those kinds of stories are in other cases of thrust faults, typically in the hanging wall area, the shattered earth stories. There's also shattered earth stories from the Kern County earthquake. And so even though there's not much data, there's plenty of macroseismic anecdotal data that would suggest it's not something that we should ignore because if we later get the data and it said, well, there's something special about this area, the rest of everybody would say, well, of course.
but Tom,
We are not.
we
ignoring.
have hanging wall effects built into the models, and they're factors of 2 or 3 increases in the ground motion. They're large factors. This whole issue is, how does that scale down to magnitude 5s? When does it go away?
When does
I
it
see.
taper away?
And
Yeah.
so we have information from the simulations that still show an effect down at magnitude 5.5. That's what we saw previously.
I see.
And Doug had explained part of it by a longer periods radiation patterns. But
So clearly those macroscopic effects,
For big-
nobody's
yeah.
observed them for 5.5.
right, and so we're trying to see, was there something empirical that we could also bring to evaluate to say, when can we say it's 0? In my model, for example, by 5.5, I deemed it 0 with no empirical or at that time simulations to help us. It looks like we brought that down in my model, it came down too quickly.
I see.
So we're trying to see what can we do to help us, but we do have all of that, all of those things are in our models.
I see.
Bob still here? So I think let's move on. So Bob will talk about the framework of the reverse cases. We haven't run the Salmons maps for those, so you're not going to see another suite of Salmons maps. But how we're going at it, and that will get to this issue of we do think hanging wall effects are very important for us to capture, and so that's part of our evaluations of the model.